Just please interrupt me if something goes wrong with the presentation like the previous time, because it might as well just be a Teams issue rather than a connections issue, but we'll see. Good morning, everyone. Very happy to be here, part of the discussion on spray flames, continuing on the same topic here. And I'll be talking about the analysis of LES results of turbulent spray flames. And I'll focus on the analysis using the two methods of POD and DMD, which should be very reminiscent of the previous time I gave a lecture on what these methods are and how they're applicable to fluid dynamics analysis that was done in our last workshop on machine learning. So I'm skipping the details of these methods and focusing more of the utility here, but feel free to ask me on how I obtained the results or how they're related to this project. Now, with that said, looking at an outline of this presentation, I'll remind you briefly on the geometry. What is the configuration that we're looking at? What design considerations we've taken and the working principles. Then I'll move on to the numerics, brief overview of how we set it up. And I'll follow with the analysis of the proper orthogonal decomposition, followed by the dynamic mode decomposition. And I'd like to also motivate at the end where I want to take this further, as there's still work in progress, I should say. But talking about the geometry, if you recall, in one of our earlier meetings, I discussed the motivations behind the UT burner, the swirler that we designed, and it is manufactured at this time. And the reason, if you recall, was the problem with the KIT burner, as we dubbed it, to the lower left with the Rand's contour I'm highlighting there. So we needed to amp up the mass flow rate through this burner so that we are more sure of the experimental margins. And the mass flow rate was the real bottleneck there. Increasing it would have resulted in a significant pressure drop across the swirler. And that was undesired, as we believed that would render the swirler pretty stable, not really suitable for studying thermoacoustic instabilities. So we went with an enlarging and a redesign of it, that you can see a RAND simulation of it right next to it. And the design is comprised of this sort of 3D shape you see on the right. I'm highlighting the primary and secondary inlets of it. So both inlets are sitting at an angle with a unique angle each one. And so each set of inlet has a different inlet angle, giving it a different swirl. And the two flows sort of merge outside where I'm highlighting we expect the flame to be anchoring. And then this renders the whole geometry also purely non-symmetrical and a complex shape, which is always a challenge for CFD. And with respect to the fuel injection, very similar to the discussion previously, this is sort of a hybrid atomization scheme. This is purely aiming the spray at the walls inside, and the film will travel further down, breaking up further into the droplets and ligaments. So that's also a very complicated hybrid atomization scheme, which I do believe you've also seen a presentation on one of our earlier meetings in Munich of the Annulite fellows. But moving on, the similar issues that Varun was highlighting in terms of fuel categorization, here also we looked at endodecane and also a mixture of it with trimethylbenzene. But we ended up going with the endodecane in the end. That's also a technical limitation with the CFD package we're using. But other than that, the discrete droplet introduction was our method of sort of sidestepping all of the film breakup and the technicalities there. So there's a lot of parameters to be assumed for whether you want a bounce scheme at the walls, what is the coalescence, and how are you assuming it to evaporate and emerge as a droplet as opposed to a film. And those have basically motivated us to sidestep the entire project and just introduce droplets where we expect the flame to be sitting. I've denoted them with arrows in one of the pictures here, where we're introducing the droplets into the domain. And another thing we're looking into is sort of a voxel meshing idea. So if you're not familiar, that would be an idea of a volumetric pixel, as you can think of. You basically pack as many elements as you can in very strictly structured fashion. And as you're switching between the more resolute part of your domain, you're switching this handoff with tet elements in between. So that whenever you have the necessity of having a finer grid closer to features of your geometry, that's how we're handling it at the moment. And for the combustion model, we're looking at the burning velocity model. We have also tried the simulations with extended coherent flame structures. But the results I'll be highlighting is burning velocity model, which also utilizes a flamelet library on the endodecane, as I mentioned, and the operating conditions of the burner. But moving along, the results of this large array simulation, on the left, I'm just highlighting the velocity contours for some of the duration of the simulation. Just want to point out the regions of activity where you can also notice kind of a flapping back and forth. If you look at the very center of the swirler, and you can see also how the flow behaves around the recirculation zones and the general flow configuration inside of the domain. I'm also highlighting the criterion, a sort of an idea on the vortex breakdown region right outside the burner. And if you look in the very center of this turbulent chaos, you can also appreciate the precessing vortex core as very prominent in this particular burner. And I'm highlighting also the OH radicals on the right as an idea for where the reaction is taking place on the right. But this was also the cross-section domain that I'll also keep highlighting throughout. As you see on the left, that is basically going through the domain. The reason you don't see the inlet ducts, for example, they're sitting at an angle, so there's no unique plane to capture all of them at once. And talking about analysis of the results, I want to bring it back to my previous discussion on the two methods of analysis that I'll be looking. And specifically, I was thinking of the analogy of a hammer and a nail yesterday, and I was thinking my motivation of going this direction was more of a finding a hammer for my nail idea. And the methods are strictly unsupervised and data-driven. And I'm not going to go into details on what they are and how they are derived, even though I'm happy to have that discussion. But it's important to note that they're very good for order reduction and clustering. So basically pattern recognition in the flow, and that's the prime motivation of using these two methods on my data. And with that said, one of the interesting features of the POD analysis is that it sorts sort of the main prominent structures of your flow in terms of their energy content. And in this case, it's a kinetic energy point of view, frame of analysis. And the very energetic mode of the analysis would equate the mean of the flow. So effectively, the very first mode, I'm highlighting this for pressure, I'm highlighting this for the OH radicals, and the velocity component perpendicular to your screen, which would show the swirl as the flow is spinning and coming out, and then the axial velocity that I'm highlighting here. And these are all strictly equivalent to a time averaged value on top of the large array simulations. But you can go further with it, and you can break it down into different modes, which I'm highlighting here for the pressure. And it's always an interesting discussion in interpreting these results, what they're showing. And it's a little bit motivated by the idea that, of course, it's energetically categorized and sorted. So that sort of primes the analysis here. But what I would say is it's easy to note that the first mode, for example, here, which technically strictly this is the second mode, is the first was the mean values. Here we have sort of pressure gradient in the combustion chamber, and that sort of is sucking up most of the energy of the analysis to its own, followed by a monopole sitting at the very base of the swirler, and followed by a series of dipoles, etc., as you go up the count of the mode numbers. And each mode comes with its own coefficient. So if you will recall, this is equivalent of saying that the result of this analysis equals mode 1 times its coefficient plus mode 2 times its coefficient, and so on, until I reached my entire full modes. And if I have a very low dimensional system, then I can describe it with a low number of modes. So sort of a filter, as you will. If I look at only the first 4 modes, I'm basically looking at the most energy content as represented in the very first 4 modes of my system. And I can also further analyze the coefficients of these. And this is what we did was analyze the modes of each, the coefficients of each mode with a Powell spectral density analysis. And it was interesting to observe that we have, for example, identified the precessing vortex core frequency of the domain exactly as we expected on the 4th mode. And this wasn't necessary before to basically extract the very points that you would expect the PVC to go through or some other method and do a DFT on it. But here you strictly have it represented in your data without having to hunt down for it. And another thing I want to highlight is the S graph, the sort of energy graph, which I'm highlighting this as an idea of representation of how much energy was present in each of the modes. And if you have a very nice decay in this graph, then you can easily say, well, I cut off my domain at that mode, sort of reconstruct my domain only using those, and filter out, let's say, the noise or the lower energy content carriers of the flow. And one thing I want to highlight here is the sort of a stepping behavior of this graph sometimes you would see. If you pay attention, for example, to the 3rd and the 4th mode, or a little bit even in the 10th and the 11th, you might see this sort of comparable energy in terms of the modes consecutively represented in this analysis, which I'll come back to in a minute. But this is what I would like to highlight on the POD side of things. Well, of course, there's a lot of different types of analysis you could do. You could, for example, look at the coefficient of modes versus each other. You could look at the representations of them under forcing and how the sorting of these will basically change or flip, sort of a sensitivity analysis on how the system is behaving and how is it responding to the external forcings that I might have. But I'd like to switch the conversation and talking about the DMD, dynamic mode decomposition analysis applied to the same data set. And here I'm highlighting the so-called DMD spectrum. So these are the eigenvalues of the decomposition, sort of showing me the time characteristics of the analysis. So POD strictly does not come with the time analysis inbuilt. It's closer to a Fourier transform in a time of in a perspective, if you will. But here we are looking at time dynamics of the system also. And I'm highlighting the very first 100 modes of the analysis, plotting them on a unit circle. And if you recall, in terms of a control of this dynamic system, if you want to look at the stability of this flame, well, then the DMD analysis, as this is a discrete time analysis, should sort of give me a within the unit circle analysis so that I know everything falling on the border or inside of this circle is rendering my system as a stable system, and I can evolve it in time. But if I get a mode sitting outside, then it's an interesting indicator of instability in the system. Now here, the first 100 modes you see also come in complex conjugate pairs, which is also confirming the sort of step behavior that we saw before. But I can also push it further and look at all of the modes of the DMD analysis that you see here of this analysis. And you can see that strictly they're all falling on inside of the circle, meaning I'm dealing with strictly stable modes for my DMD analysis. And this is the sort of an interesting idea of whether you would actually see modes outside of the circle had you had an unstable simulation or not. Something I'm looking into at the moment, but it's an interesting indicator of stability of the system also. Even though again, the interpretation of what each of these modes mean and also how they relate to the POD analysis. Also, if you look at the literature of applying POD and DMD to flame transfer functions, you would see that it's a little bit of a subjective manner, how you would interpret each result, how it relates to each of the POD modes, etc. But I'd like to also highlight that the time dynamics allows me to evolve my system in time. So this should remind you of the previous discussion that I had on this, that on the left, I'm basically taking the velocity field of the LES analysis, and I'm performing a full-on no truncation DMD analysis on it, and I'm reconstructing the flow field again. And that's what you see on the left. And this is interesting, as if I showed you the actual data set, would look exactly identical to that. That's why I didn't even include it at this point. And the first sites cutting the region on the most energetic modes of the system is an interesting idea than what you see on the center of the in the middle animation. And that's where the first 100 modes that I highlighted before are basically truncated, and the system is reconstructed only using those 100 modes. And to further push this idea, you can also take this time dynamics and evolve your system past its final timestamp of the simulation. That's what you see on the right. So I have, let's say, half a second of CFD simulation. I can extend it however long I wish, as long as my system is stable in the representations of the DMD modes. That's what I get on the right. And that's a little bit of a peculiar thing to do, I would say. Last time we also had some discussions on the validity of this analysis. It is as good as the data was, and the more periodic the system was, then the more faithful this sort of prediction and extension into the future is. But I'm interested in seeing whether this sort of analysis can help ameliorate the fact that we have very expensive simulations, and whether we can sort of highlight an instability in the flow by such methods and looking at the modes in this manner. Now, I can also look further into the spectrum representation of the reconstruction. So here I'm showing 4 points of my domain, as highlighted in the picture on the left. And for each of these modes, the blue graph is basically the CFD simulation on the velocity field. And we're looking at the vertical component of the velocity here. And on the yellow graph, I'm basically looking to reconstruct this flow field only strictly using the velocity component on the vertical axis. But the other sort of orange/red graph is reconstructing the same using more information in the domain. This is sort of a proof of concept that the more information you include in the DMD analysis, then closer and more faithful you will reconstruct the data.
You're running out of time, Alireza.
Yeah, sure. I'm on the last slide right now. And this was sort of an idea to highlight DMD predictions can be very powerful, especially for CFD analysis, since we have an abundance of data, and the more we represent them in the matrix of DMD, then the more faithful the reconstruction can be, and hopefully that can sort of hint at where the system is evolving towards. And just to finish up here, the main idea as this relates to the flame transfer functions is sort of an idea on what is the representation of each of the modes of these analysis as they appear on the flame transfer functions. So that the more modes you include in this analysis, the more you converge towards the final frame transfer function of the analysis. And this interesting idea, the one that I'm currently working towards, and also multi-resolution proper orthogonal decomposition is interesting, so that if you have a very concentrated activity in your field, you can extract the frequencies associated with it. You don't have basically it sort of averaged in your domain and sort of lost in the grand scheme of things happening in the burner. But with that, I'd like to conclude, not to spend much more time on this, and thank you for your attention. Looking forward to the discussion.
Thank you, Alireza.
Thank you, Alireza. Shame, poor Alireza. I think he was still in time. It's just because there were many questions before he started.
I know.
Yeah, I expected this, Bridget.
You skipped the slide about your cooperation with the other fellows.
Well, yes, it's kind of a mix. The cooperation is mainly with Sara in terms of designing the